Okay, great. So this is the last talk of the day. So remember that right after the talk, so there's a wine reception next door. And so the last talk will be given by Nial Friel from University College Dublin on optimal Bayesian estimators for stochastic block models.
Okay, so thank you, Francois. So thanks for the invite and to you and to the organisers. Okay, folks, so yeah. So my talk is about optimal Bayesian estimators for stochastic block models and latent block models, and in general for latent variable models such as finite mixture distributions and so on. So this is joint work with my PhD student Riccardo Restelli. Okay, so here's a kind of cartoon picture to show you what we're trying to do here. So we're considering a latent variable clustering framework, so it might be finite mixtures, it could be stochastic block modeling, etc., where we get a posterior sample of partitions or allocations or memberships. And what we want to do is we want to somehow summarize the set of partitions that we get in some way. And we want to ask also the question, what is an optimal partition in this kind of setting? So here we got some output from, it turned out to be a finite mixture model. And you can see that we get different numbers of clusterings and hence partitions, both in terms of the number and of their allocation across the different samples. So it's not a straightforward task how to summarize that output. Okay, so to continue the overview, we're going to take a Bayesian decision theoretic approach to define our optimality, and we want to try to find something fast and context independent in terms of the models that we can apply this to. We'll end up using a type of greedy algorithm to find the best partition. And one of the sort of nice outputs of our algorithm or method is that we can also select optimally the number of groups as well as their allocation to the observations to those groups. We're going to talk about the choice of loss function and hopefully show you that this can accommodate a variety of models. And because this is a meeting on networks, our focus will be particularly on the stochastic block model and also so-called latent block models. Okay, so a kind of a generic context here is where we have observed data X, and each observation X has got a certain attribute associated to it. So each individual has an associated unobserved cluster membership value or allocation. So each xi has got an underlying zi, where zi takes values from 1 up to capital K for each of the capital N observations. And so zi determines the distribution of the observation related to observation I. So examples that this kind of setting falls into include finite mixtures. So the z is the allocation for the ith observation, infinite mixtures, hidden Markov models, and our particular focus, as I said, is on block models for networks. Okay, right, so here's an example of typical data that one might examine using the latent block model, which we'll get onto a little bit later, for bipartite networks. So in this example, it's a well-known and well-studied data set of how some congressmen voted on certain issues in the US House of Congress. And the idea here is that one wants to cluster both the columns of this matrix and the rows simultaneously to find out which congressmen tended to vote in the same way on a certain number of issues. So it's kind of joint clustering of rows and columns, sometimes known as biclustering, sometimes known as co-clustering. And the main questions here are how many row clusters are there? Also, how many column clusters are there? And what is the best partition of nodes to those variable row and column clusters? Okay, right. So the Bayesian decision theoretic approach is to define a loss function, which is on the z cross z, takes z cross z onto the reals. So it's a loss function with arguments as two partitions a and z, and it quantifies the loss when the decision is a, while the true partition is z. Okay, so the decision A star is a Bayes action if it minimizes the expected posterior loss. So psi of A defined to be the expected loss, A is Z, where Z is from the posterior distribution. Okay, so we can write that as a sum over all possible partitions Z of the loss times the posterior of Z given the data X. Okay, right, so we know that you know, in practice when we think about Bayesian estimators, so for example the map, it has an underlying loss function, which is in this case the 0,1 loss, which says that the loss is 1 if A doesn't coincide with Z, even for a single observation. Okay, and 0, that's the wrong way around, isn't it? So the loss should be, yeah, no, that's fine, that's fine, that's fine. It's fine. Yeah, so we give it a sort of maximal loss, even when they differ by a single observation, and 0 when they're identical to each other. Okay, the posterior mean has got its loss as a mean square loss, mean square error loss, and again, for partitions, that doesn't make a lot of sense, that averaging. Okay, so what is often done is to base a loss function on the contingency table for two partitions. So what we've sure.
The classification error, right?
Yes. So sort of observation-wise. So okay, what this tells us is we have partition Z with classes 1 up to kz, and partition A with classes 1 up to ka. And the entries of this table count essentially the number of times that observation I in partition A is set to G, and observation I in partition Z is set to H, and added over all observations. So that's what the entries here tell us. And the row sums give us the sort of marginal counts of the elements in partition Z, in this case set to class 1, up to the elements in partition Z set to class kz. And there's capital N of them in total. Okay. So, please.
So, can you go to the previous slide? You said mean square error does not make sense. Why?
Say again?
You said mean square error. You don't like mean square error loss, and why?
Because Z is a discrete valued.
You know, just count. You know, discrete value is just counting the number of mistakes, right? It is a discrete value, but that's equivalent to having distance.
Well, so I suppose when we take a finite sample to estimate that expectation, we don't end up with a quantity that's itself a partition.
But there's another issue if the labels of partition get changed.
Oh yes, the label switching issue.
Label switching messes up mean square error.
Of course, you have upward permutation.
Yeah.
You could define upward permutation.
Oh yeah, I mean, you would have to correct
Right,
permutation.
yeah. You know, you look at the minimum permutation, then so on.
Yeah.
So there's, yeah, I mean that's, there's a second issue too. So. Okay, so based on this contingency table, what's often done is to consider various quantities associated with let's say the probability mass function associated with this kind of, think of this as a joint distribution normalized by capital N, or the column totals again as a probability mass function, or the row totals as a probability mass function. So we can think about the entropies of each of those quantities, so HA, HZ, and the joint entropy for A and Z together. Okay, so the mutual information can be evaluated from the individual entropies for HA and HZ and minus the joint. And the particular loss function that we're going to focus on is what's called the variation of information loss. So it's defined as twice the joint entropy minus the entropy for A minus the entropy for Z. Or equivalently, we can write that as the joint entropy minus the mutual entropy. Okay, and it turns out that this has been a well-studied loss function, particularly by Marina and Mela in 2007. And different properties that it have include the fact that it's a metric and satisfies triangle inequalities, and so on. Also, importantly, it's invariant to label permutations. So if you change any of the labels here, any of the class labels in the rows or in the columns, the loss that results using the variation information is the same. So that's a nice property that it has. Secondly, it's got this local property that if A is obtained from Z by splitting one cluster into two, so it's sort of locally changing the partition, then the loss only depends on the cluster that's been split. And that's kind of nice. That turns out to be nice when we do the minimizing the expected loss. Also, the VI loss is always smaller or equal to log n, and it's 0 if A is identical with Z, up to permutations of labels. Okay, so other related loss functions related to the variation of loss is the normalized version of it, where maximum value is now 1. Normalized information distance, and a loss that I want to spend a few minutes talking about, the Binder's loss. So Binder's loss penalizes the loss resulting from allocating two observations to the same cluster when they should be in different clusters, and vice versa. And it turns out that Binder's loss has got can be expressed in terms of the quantities from the contingency table that I showed you before as well, in the following way. And it turns out that Binder's loss is closely related to what's called a posterior similarity matrix, which I'll just describe to you now. So a similarity matrix associated to a partition, so it's a capital N by capital N matrix. N is the number of observations in the data set. And the matrix has a 1 where two pairs of observations are classed in the same group, and it has 0 otherwise. A posterior similarity matrix is one where the entries of that ij matrix, so the probability that entries or observations I and j belong to the same cluster or group. So the connection then between Binder's loss and the posterior similarity matrix is that Binder's loss corresponds to the Bayes action that minimizes this following sum. So the indicator that observation I is in the same group as observation j. And here Bij is the ijth entry of the posterior similarity matrix. Okay, right, so there's a sort of history here behind this Binder's loss. It was first exploited in Lau and Green in 2007, and more recently in the context of Bayesian nonparametrics, Wade and Garamani also looked at it. And what they observed is that Binder's loss typically overestimated the number of groups. And they also focused on a variation of information loss, and they take a different approach to us in that they approximate this psi a, the expected posterior loss, using a Jensen's inequality to make it practically work. Okay, so here's what we do then. So we need to simplify because the set of partitions is huge, and calculating the expected loss is a really challenging thing. So what we do is we sample from the posterior, the marginal posterior for Z. We get a sample, capital T partitions. And then for every partition, we look at this sampled average loss for a given partition A, and then try to minimize that function. So we're using the same partition throughout the algorithm, as opposed to the kind of correct thing we should do is for each action that we consider A, we should generate a new sample. But we use the same sample for reasons of scalability. Okay, so the greedy algorithm has a sort of skeleton sort of set up as follows. I should say we input a maximal number of groups, and we start with a random initial partition, and then we do a kind of greedy kind of move where we reallocate every observation in turn, moving it to a group that minimizes the expected loss. And we repeat that over and over again. And it turns out that because of the nice property of the VI loss, that if we split a cluster into two, we only need to worry about the change in loss for those two clusters that are affected. And the overall complexity of the algorithm turns out to be T, which is the posterior sample size, N, the data number of observations, and K, the number of groups. Okay, so finally to look at some models where this can apply to. So stochastic block model. So we have capital N nodes of a graph, and our adjacency matrix, 1 if there's an edge from I to j, and where edge probabilities are determined by their latent allocations. So pi gh is the probability that xij is 1 given a latent variable zi is in group G, and a latent zj is in group H. So pi is a generic element of a k by k connection matrix, capital pi. Okay, right. So the likelihood of the network is then expressed in the following way. So we have this kind of Bernoulli expression here. Product over all observations for all possible group labels. And we assume that the allocation variable Zi follows a multinomial distribution, and we put a conjugate Dirichlet on it. And moreover, the pi GHs themselves, we put a beta prior on those two. And that makes everything conjugate, and it allows us to write the posterior probability of the number of groups and their allocations in a closed form. And we can sample from this thing to get a sample of partitions, which we can then apply our greedy algorithm to. Okay, so one of the important consequences of working with a marginal posterior like so is that the vector z is of fixed dimension. And this means that we can explore the number of groups without using transdimensional reversible jump algorithms. So this allows us to explore the uncertainty in K. And Nobile and Fernside sort of set up an algorithm to do this kind of thing in the context of finite mixtures. And in work with MacDade and Brendan Murphy and myself, and also with Pierre Latouche, who's here, we looked at how this can apply to stochastic block models. Right. So here's a data set where we apply this stuff to. So the data set consists of 196 nodes and 3,000 odd edges. And the nodes represent blog host names, and the edges are the hyperlinks that connect pairs of blogs. And this is data collected on a particular snapshot on a particular day at some point in the past. So the political affiliations of the different bloggers are known, and the main political parties are given as here. You recognize these?
Wouldn't call UNP the French. I'm not sure it would be hacking.
Maybe this is from a few years ago. I don't know.
They renamed themselves as Republicans.
Okay. So what we do? Okay. So to sample from that posterior, to sample a collection of partitions, we use the algorithm presented in this paper by MacDade et al. So we collect 10,000 samples, thinned by 100, and we run our algorithm 100 times to see how it's the output from it. And it turned out that in 10 of those 100 runs, we reached the same optimal value. In terms of CPU time, this is typical of what we've observed, that the MCMC sampling is much more costly computationally than the actual greedy algorithm itself. And to compare as a reference, we also looked at a variational algorithm implemented in the mixer package. Okay, so some output. So this is the posterior distribution for the number of groups, and it has a mode at 17. And it turned out that our VI Bayes action gave us a partition with 18 groups. So it differs from the posterior mode for the number of groups. And here's a trace of the expected posterior loss as a function of the number of steps of the algorithm. Right. So here's a rendering of what the variational output looks like. It shows 11 groups, while our VI Bayes action chose 18. So a finer partition than what was returned from the variational algorithm. Okay, so this shows you the adjacency matrix for the variational action, and side by side the adjacency matrix for the VI Bayes action. So these red dotted lines show you the groups and the rows, and obviously the columns too. So you arguably see a better kind of blocking structure here than for the variational action. Also to show you a confusion matrix for the four main political parties, and to show that the grouping here tends to discriminate in some way the different parties, at least the four main ones. Okay, right, so the final example is a so-called latent block model. And this is one that can be used to model bipartite graphs. And this is, think back to the congressional problem I showed you at the start. The problem here is that we want to cluster both the rows and columns of that non-square potentially adjacency matrix. So we have two partitions, R and C, for the rows and columns respectively. And the number of groups for both rows and columns are this variable number KR and KC respectively. These are unknown. And just as for the SVM model, we use a multinomial Dirichlet conjugate setup to allow us to marginalize. And similarly, the edge probabilities, given the row labels and the column labels, take this value pi GH, and we put a beta prior on it too. Okay, and just to say that, that for this type of model, you don't necessarily need to restrict it to binary data. It can apply to other types of data, so Gaussian data, Poisson data, etc., depending on the context of the problem. So here the likelihood given given a partition R and C and the connection probabilities pi has again a similar kind of form to the SBM model. And again, the pi GHs are modeled as IID beta random variables. This allows us to get a marginal posterior for the number of row groups, number of groups in the rows, columns, and the two partitions R and C. And we can sample from that then, and that sample is then used inside the greedy algorithm. Okay, so the congressional voting data. Data records 435 members of the Congress voting yea and nay on 16 key issues. We also know the underlying political affiliation of those 435 congressmen. The data arranged into a bipartite network, where we got two node types. One is the Congress members, and the second is the voting issues. And we convert that into an adjacency matrix, with ones denoting yeas and zeros nays. So here's what the data looks like. And the question for us is to try to, in some way, permute the rows and columns so that we see some sort of blocking structure in the data. Okay, so what we do is use an algorithm in a previous paper to sample these allocations from the posterior. We sample a collection of 10,000 of them, 10 by 100, and we run our algorithm 100 times, and we've observed that in 65 of those hundreds, we get the same optimal value. And as before, the MCMC sampling is the expensive part. As reference, we also look at the partition with the highest posterior value. Okay, so this is the posterior distribution for K, number of congressmen who were the clustering for the congressmen. It has its mode at 6, and also the VI action had the same number 6 groups. So again, the EPL values, expected posterior loss over time, decreases reasonably quickly. Okay, so the confusion matrix in this case seemed to separate out very well the Democrats and the Republicans into groups 1, 2, and 3, and 4, 5, and 6, respectively. Okay, so this is the picture. The map shows you the following kind of blocking, and the Bayes v action is here. Again, not sure how much you can kind of get from that picture, but so finally to add a quick comment, and that is that when we generate a sample of partitions from the posterior, often the number of unique partitions is smaller than a reasonable fraction smaller than the sample size itself. So what we can do, although it's expensive to do so, we can summarize the unique partitions as z tilde 1 up to z tilde t, and we can look at the counts telling us how many times each of these different partitions occurred. And and having done that, we can write psi of a as an average over these t tilde terms, weighted by the frequency at which that partition z tilde occurred. And it turns out that Strel and Ghosh give us an efficient algorithm to actually figure out what those unique partitions are. And this typically gives us a computational saving. And in the experiments we've looked at, we found that about 20% of the samples were not unique. So we get some kind of saving here. Finally, just to conclude, finding summaries of sample partitions is challenging. And Bayes' decision theory gives us an optimal criterion for clustering. And the greedy algorithm gives us a way to estimate that optimal partition. Applies to network models and finite mixture models, et cetera, And here is the archived paper. And here's Nial's paper on the VI loss, Wade and Garamani's kind of method, which is applied to nonparametrics. And here's the paper by Nobili and Fernside, where they show us how to do this integration for finite mixtures. Okay.
So, Niall, in the clustering or literature on assessing partitions, for better or for worse, the adjusted rand index has become the kind of standard that's widely used. And so I'm wondering do you have any comments on the VI versus adjusted rand index, and could you use adjusted rand index or other measures? Could you just plug it in to your method?
So the rand index is it's closely related to the Binder's loss, and that's a result of Marina Mela. It's kind of like a scaled version of it. So I expect that the Binder's loss, the rand index would behave in the same way as Binder's loss.
That was a very interesting talk. I wondered about your beta prior on the edge probabilities. Does that give a dense graph in the end?
So we used a beta, I think a half.
Yeah, if you say a half.
I don't know is the answer. I haven't simulated networks from that. But what I can say is that in the setup of our problem, we need to fix the hyper parameters throughout the experiment, but what we really should do is put hyperpriors on those two. But makes the algorithm even more complicated. But
I mean, there's a range of entropies called Salis entropies from Shannon, alpha equals 0, and then gamma equals 0, and then Rennie 2 is when gamma equals 1, all the way up to the maximum. I wonder if you'd experimented with a kind of a range of different, within that fairly classical
no, so our
spectrum of entropies. Because I think you had Rennie entropy when you have the pair. One of them should look like Rennie. When you had the two at a time one, I didn't quite understand it, but the two at a time stuff. And you had a, can't quite see it there, but anyway, I think you had it somewhere.
no, we pretty much exclusively worked with this variation of information loss, but I mean, yes, there's a host of related entropy-based loss that one could think of it.
Thank you.